Okay, we will get underway with the final day and the exciting conclusion to Georg's lectures on matrix models and their simulation. Look forward to it.
Thank you, David. So today I will review some results of the lattice simulations that have been obtained with the matrix model. I won't be able to cover really also the two-dimensional case, which is also very exciting, but I will rather focus on this one-dimensional BFSS model and investigate in particular one specific question in the simulations, namely the energy that, the average energy that has been computed and compared with the gauge gravity duality. But before I go into this, I will briefly go through the things that we've covered in the previous two lectures. And because I will have to go back to these kind of topics when I discuss the final results. So what I've done is basically I first covered the theoretical background, so investigated, explained the matter content of this matrix model, which is mainly the BFSS model, and then also this modification with an additional mass term that does not break supersymmetry completely, which leads, if you add those two, then to the BMN model. Then I discussed the first appearance of this model in terms of this D-brane, in terms of this 11-dimensional brane theory introduced by David, Nicolai, and Hopper, and which was a nice theory, but it led to the appearance of instabilities in this membrane that were later discovered by David, Lüscher, and Nicolai. And then we went on towards all the kind of string theory conjectures, gauge gravity conjectures, where this kind of model plays a role. And in particular, there are two basic appearances. So one of them is in terms of this brane theory, where you have a duality between the D0 brane theory and then corresponding gravitational theory. And the other one is this conjecture about the relation of this BFSS model to M theory. And this led to this kind of conjectures phase diagram where you have besides a perturbative part that is completely separated from these parts that are interesting for gravity duality, so which appears only for small couplings. Then you have a part where you have this duality to type 2 string theory. And then apart from that, there's also this possibility to have a connection to M theory and different phases, in fact, of M theory, depending on this, how this theory behaves on this additional circle in the 11th direction that builds up if you go from type 2 to this M theory. Then after discussing all of these kind of properties of the theory, we went on to the discretizations, and I discussed basically all kind of supersymmetry realization on the lattice. In particular, I've shown that you can implement part of the supersymmetry on the lattice. You can find Q-exact formulations on the lattice with a supercharge that squares to 0 on the lattice. And this kind of, and you had also the possibility to go to a completely non-local formulation and have an completely intact supersymmetry on the lattice. And in this one-dimensional examples, it's not forbidden to do all kinds of different, to try out all of these different kinds of investigations. One has only to be careful with the possibility that you can have certain artificial phases that appear for this kind of theories. If you go to the gauge theory, it becomes a little bit slightly more complicated. You have not the possibility to have a formulation that completely keeps the gauge, the supersymmetry on the lattice, but you can still use this momentum space formulation that has been also applied in simulations of the BFSS model. And in addition, there is also a rather standard way to discretize these theories. I've also discussed that improvement seems to be very important if you want to go to towards precise results and make all kinds of extrapolation to the large N and continuum limit for these theories. And then I mentioned also that due to this brane instability, you have problems with the flat directions, and you need to find a possible way to handle this divergence if in the simulation this flat directions are explored. Now I want to add just a brief note concerning these realizations also towards the two-dimensional theories. So in 2 dimensions, you have also super renormalizable theories, and it was brought forward by an example by Goldman and Petcher actually a long time ago in a two-dimensional Westomino model, where they really showed that you get to where you can use these perturbative calculations to control the fine-tuning. So you can calculate the fine-tuning that is needed to get towards the supersymmetric continuum limit. And this perturbative fine-tuning is enough to recover supersymmetry in the continuum limit. Most of the simulations that have actually been done in these two-dimensional theories, Super-Yang-Mills theories, actually follow the approach of keeping part of the supersymmetries intact on the lattice. There are only a few studies where you try to do this also with this fine-tuning approach, because still it's a complicated problem to calculate these tuning coefficients in this supersymmetric Yang-Mills theory. It's more complicated than in this gauge, in this ungauged Westomino models. Now, I want to go a little bit through the development of the simulations, how they evolved in time, and how more and more precise results have been obtained from the simulations. The first investigations actually in this gauge gravity context were with the simpler model, this zero-dimensional IKKT models, and there you can really also do a lot of theoretical analysis concerning the matrix integrals that you have. But I must say that the IKKT model is still turns out to be so complicated because, for example, the Pfaffian phases play an important role. This is still under investigation. So we had here research talks that have explained this. Then in the beginning, there have also been quite interesting approaches using Gaussian approximation to investigate these theories. In the later steps, there have been technical developments that started first with simpler Westomino models in order to establish the techniques to simulate supersymmetric theories. And then first investigations mostly involved the theory with lower part of supercharges, as for example done in these studies here. And also precise numerical tests were done with simpler models where you just leave away the fermions and you can simulate the theory without any, with a much larger statistic and much larger precision. As has been done first, I think this was the first study of these Monte Carlo simulations of the bosonic part of the BFSS model in this publication in 2007. Later on, the focus was really on verifying that the simulations work and check that you get consistency with the Gauged gravity duality. But as I will show later on, the Monte Carlo techniques left this part and really became a tool to derive new concepts. And the most modern development is to go into the direction of quantum computing and deep learning and apply techniques that go beyond the Monte Carlo simulation in this context, as has been summarized here in this paper. So if you want to simulate the BFSS model, you first need to consider your parameters. And usually in Lattice QCD, you would have to set a scale. You would have to measure a scale setting parameter. But actually in this quantum mechanical models, everything is set basically by the dimensions, by the dimensional coupling that you have in the system. That's also why temperature and energy usually are just expressed in terms of the units of this one coupling. And you can also then, and the temperature can then be, is of course related to the inverse of the lattice extent in this one temporal direction. And this gives you then also something, some estimations of the lattice spacing. So you can have as input parameters the temperature, the coupling, and from this you can determine then, and the lattice extent, and from this you can deduce the lattice spacing, or alternatively you can input the lattice spacing and deduce the other parameters. In the BMN model, also this dimensionful mass parameter is usually given in units of this, of this one coupling. Now, what kind of observables are investigated on the lattice? So what one usually looks at is the energy of the system. You can use, and this is related here to this part of that you can use by subtracting some parts that you just get from the integration of the, by subtracting some constant part that you can compute here in this part. So it's just related to the bosonic part of the action if you do a transformation of the fields. And then you also can look at the want to monitor, of course, signals for confinement, deconfinement transition, and this is done in terms of the Polyakov loop, which is the product of the links in the one direction, and is of course expressed in terms of this eigenvalues if you go to the static diagonal gauge. In addition, what you have to monitor usually is a kind of signal that tells you whether you have some signature of the flat direction, which is the square of this, the trace of the square of this X matrices. You can look at, it's often very good to look at individual contributions, because due to lattice artifacts, certain directions can be more enhanced than other directions in this flat directions. But if you just want to look at if the flat direction are a problem, then you can just look at this overall term. And then, of course, you can, another interesting observable that is usually investigated is the potential, which comes from the commutator term. Now, the gravity prediction, you can derive a prediction for the energy as a function of temperature from a solution of the near extremal black hole. And
maybe
yeah.
On the previous slide. Yeah, so from the expression for energy, have you thought about computing the partition function as a numerical integration? Is it possible?
You could do this. I mean, in Lattice QCD, this is a way that usually these kind of expressions are calculated. So from the derivatives of the partition function, you can derive thermodynamic quantities. But as I think this has not been done so far. So you can try to integrate this.
Okay, so it's a straightforward process.
Yeah, I mean, yeah, usually this, yeah, okay, there are technical details. If you go to the corresponding QCD simulations, you have to subtract certain contributions there from the zero temperature, and this leads sometimes to problems because you have near cancellations and only a small effect. This is what I know from the investigations of QCD of these kind of quantities, but I'm not aware that one has tried to extract these thermodynamic properties as well.
Okay, thanks.
Okay, and from these, so what this basically tells you is that from the gravity side, you can also derive a kind of setup where you introduce a temperature which is related to the Hawking temperature in this D0 brane solution. And then you have also the entropy, and from these investigations, it has been derived that they are a prediction for this observable that I've defined previously, the energy divided by n squared. And this is a rather interesting observable because it gives you something that you can nicely check on the lattice in order to verify that you are in a regime where the gauge gravity duality holds, and in order to verify and precisely check the gauge gravity duality. Actually, this has in the theoretical developments of this on the gravity side, one has been able to go even one step further and derive corrections with some, in some case, unknown coefficients for this kind of dependency of this energy observable on the temperature. And so you can have a very precise check not only of the leading dependency, but you can also check whether you are able to capture subleading parts. And these, overall, this gauge gravity duality picture, as I've shown you already in the summary of my previous lectures, should apply always in the regime where the temperatures are quite low, and from the it has been usually expected that in this kind of pictures that the M theory becomes relevant then in the very low temperature regime, where you really see a transition then from this type 2 theories to the theory to the 11-dimensional theory. But I will come back to this in the discussion of some later results. Now, the first investigations, as I said, have been done for the Bosonic BFSS model. And in this case, you are you expect that the theory shows a phase transition at a finite temperature, whereas this should not be the case in the BFSS model. And the high temperature regime should at some point also lead to a good approximation of the BFSS model. But of course, you are not interested if you are looking at the gauge gravity duality in this very high temperature regime, but rather in the low temperatures. This kind of model has also been used in investigation of what is called the partial deconfinement hypothesis, and also related to the Gross-Witten-Wadia transition, but I won't be able to cover this in this introductory talk here. What I will rather focus on is how well in the simulations with different actions and different approaches, these kind of overall gravity picture has been captured. So the first simulations are shown here. And in fact, this has been done not in this standard approach as one would expect, but rather in this momentum space formulation of the theory. It has been verified that this theory stays in the confined phase in the range that has been investigated. And as you can see, these simulations were done on rather very small lattices. So in this momentum space formulation, as I told you, corresponds in fact to a lattice formulation. And the number of lattice points roughly should be 2 times this lambda plus 1. So these are really very tiny lattices that have been investigated here. But it's remarkable that nevertheless, the high temperature regime can be just obtained from the perturbative estimates. But that it's already been possible to go beyond this perturbative approximation and then approach towards here this black curve with this, which is the gauge gravity duality prediction. And the temperature range is also quite low. Now, you have to look always how the instability problem in each of these simulations is avoided. And in this case, it has been avoided by going to rather large n of the matrices. And the claim in the paper was basically that if you go to the large n limit, then the instability won't be a problem. This has been different if you go then to the reference is not in here anymore. So this is what have been the first results by Simon Catterall and Toby Wiseman at 2009 of this same theory, and they really brought forward that it's very important to capture also this instability, that it's really a physical property of the theory, and that the only way to make sense basically of this theory should be to regulate somehow this flat direction, which is done here by adding an additional mass term. Now here, several different n has been investigated, but you can see that, and in contrast to this quantity that I've shown before, this is the quantity divided by the temperature. So the high temperature regime where you have a nearly linear rising here should correspond to rather a flat behavior. So there's no contradiction between these results and the previous data. But you can see that first of all, the extrapolation to the large n limit seems to be rather challenging from these data. And you can also see that the differences between if you go with a parameter to 0, that this really plays a crucial role. Now, in later studies, the investigations of this momentum, so this also to add, this has been done with a standard lattice implementation, which is also different from the other approach. And then this momentum space implementation has been brought forward and has been much further investigated. In this case, extremely low, in the next step here, it has been possible to reach extremely low temperatures in the theory, but it's a little bit questionable how well controlled this is, because in this investigations, an additional potential term has been introduced, which adds basically a cutoff of the in the flat directions. You have a term that basically forbids any kind of further walk away in these flat directions. But on the other hand, all of these results seem to be very consistent with the low temperature results, and it has been even possible for the first time to investigate the first order corrections in 1/n² in this theory. Now, later on, there has been a Q-exact formulation on the lattice, which shows a very good convergence to at low temperatures to the gravity prediction. It also seems that there are rather small corrections to the continuum limit, even without doing much extrapolations here. The differences, of course, which could also lead to different lattice artifacts, that in this case, in comparison to this cut in this previous investigations, there have been a mass term introduced and a controlled limit towards the zero. Mass going to zero has been performed. And the first very precise results have then been obtained at 2016 in this publication by Evan Berkowitz and et al. And this have been, with these very precise data that have been obtained in this investigation, it has been possible for the first time really to get towards higher order corrections in this expansion, in the gravity prediction, and even to calculate coefficients that have not been predicted directly from the gravity side. So that was a great achievement, and so this basically shows that one can really go from the way where gravity has been just used, this gravity predictions have been just used as a verification of the simulation, towards really to use the simulations to predict something that has not been calculated yet on the gravity side. So this was a great achievement that has been done here. Just to summarize what has been done there, it has been improved, as I explained in this concerning the different lattice discretization. It has been a certain way to improve the lattice action. A certain tree level improvement has been added, and it turned out to be very important. Then the flat direction has been suppressed by going to larger n, and not with additional mass terms or cutoffs. And this basically has restricted the number of temperatures that have been possible to investigate in this kind of analysis. And in particular, the low temperature range that has been achieved with this explicit cutoff has not been possible to reach within the reach of these investigations. And there has been a controlled continuum and large n extrapolations done here from n values of n that are within the range up to 32, and lattice sizes that usually went up to 48, but in some cases even a little bit higher. So these are the kind of parameters that you have to use to get to these precise data. I just want to add here as just the result that Stratos has added to this talk. And this is very interesting because while these results of this precision data are in this range here, so one might still wonder whether the gravity results is finally approached, that these new results as Stratos presented really go towards a point where within errors you achieve consistency with the gravity prediction. The main additional improvement here was that basically this has been achieved by extrapolations from the BMN limit. But much of this has already been covered in the talk by Stratos. Now, this is basically one of the first and most important verification that the simulations have worked and that we are really able to capture the physics of gauged gravity duality and make precise in checks of whether this gauged gravity duality works for this low-dimensional matrix models. Now, one can use this tool also to conjecture about possible additional things that or about the physics of this this BFSS model and things that have not so far been considered with the gravity side. So one thing is a conjecture that has also been mentioned in or discussed in more detail in Stratos' talk, and this is basically the connection to the M-theory phase. Usually, as for example explained in the paper by Simon Catterall and Toby Wiseman, is that one thinks of M-theory to become relevant only at very low temperatures. In this work, a rather different picture was brought forward, and this is that these additional M-theory-like phases should rather correspond to some unstable or metastable phases that are present if you think of a kind of first order like transition behavior at the very low temperatures, so that you would have, instead of an absolute minimum which correspond where this 11-dimensional theory plays a role, where this is just a metastable minimum that is present in the theory. And besides the usual deconfined phase that you expect to persist even to very low temperatures in this theory. So this is just one example where new ideas have been conjectured based on the results of some numerical investigations.
So if I could ask a question about those cartoons there, they almost look like that they're making the partially deconfined label look analogous to a sphaleron sitting at the tunneling barrier between the two phases. Is that a productive way to think about that sort of thing? Because it's not one I
mean, you should think about this as a maximum of the free energy, and it would be rather something that you would see in a microcanonical ensemble. These kind of additional features that you investigate here, and so it's just something that you expect if you would have some first order transition where this becomes more transparent than if you just have a metastable phase. Here there are actually two not only this kind of spaleron, which would be really some highly unstable point, but you also have this additional metastable point, and this you need to have this intermediate point. So yeah, basically you need an additional maximum if you want to have two separated this additional maximum, and in this work it has been conjectured that this should correspond to some unstable state also on the gravity side. So basically, this is what I wanted to tell about the main results for the BFSS model in this rather educational introduction here. That the numerical data that has been available now shows now good agreement with gauge gravity duality, and that the low temperature regime that is important really to have this this connection to gauge gravity duality has been possible to reach in this simple one-dimensional theory. Now it has even been possible now to get from this just verification phase to something where you can go to predictions of gravity corrections that can newly be computed or confirmed. And I have to add that also the computational costs, and I mentioned this already in this in the last lecture, that this computational cost is usually higher than you might expect. So these simulations, this precision data that I've shown here, are usually computed on moderate clusters, and you need quite a long time to get enough statistics and to have problems like especially like the flat directions under control. And I've also shown in the end that the lattice simulations can be used as a tool to test and develop new ideas. In the very last part, I want only to add briefly also something concerning the differences if you investigate this BMN model in more detail, because this BMN model has a richer phase structure, and because it has an additional parameter, of course, and this parameter has the nice property that you can go to the large mu limit where you can do basically perturbative calculations, and you can estimate in this perturbative calculation a critical temperature for deconfinement transition, and even corrections to this leading order behavior have been calculated. There have been basically only 2 simulations of this full BMN model. One of them were done by Simon Catterall and collaborators, and then the other more precise investigations were done by Denjo and his collaborators. There have been more investigations also of the bosonic model, but which I won't discuss here in detail. Now, as I said, this model has a more interesting phase structure, and this is due to the fact that you can have phases where these additional terms that you add to the action become more relevant and get a significant contributions, and this is usually determined by this Myers observable, whereas I had in the beginning this I run only over the first 3 indices of the summation. And here you see this signature in this studies that Danger and collaborators have done for the Myers term at a critical value of the temperature. And they were able to determine this transition of this Myers transition and also determine in addition the deconfinement transition. And so basically in this BMN studies, you have to consider two different phase transitions which get separated at larger mu values. But if you go to lower mu, then you always, they found that this transition these two transitions merge, and you have basically one transition where you have both the deconfinement transition and the Myers transition. But at larger mu, this separates, and the Myers transition happens usually at a higher temperature. So far, these investigations have been done in great detail and with a rather high precision. Maybe the size of the matrices has been quite small, so there could be still some room for improvements in further investigations that are that lead to a better picture, especially in this low temperature range. Another thing that I want to mention concerning the new things that have been developed and have been inspired also by lattice simulations is the gauged-ungauged correspondence. If you look at the system in a static diagonal gauge, this is basically something that seems to be quite obvious, that somehow if you go to a very large lattice extent, then these in the static diagonal gauge basically become just kind of boundary terms, these additional contributions. But there has been a much more detailed analysis of this effect on the gauge gravity, using gauge gravity duality on the gravity side. And there they have conjectured that you have a certain exponential behavior, and that at low temperatures, basically the gauged and ungauged energy this energy observable that I mentioned, that this should converge to each other. And this has been confirmed in a detailed investigations for the BFSS model and later on also for the BMN model. This is, I think, a very interesting and new development, because it also might lead to a better way to identify certain observables in the BFSS model, which because you always have a problem in the BFSS model if you want to look at the matrices and sub-matrices of the X fields, because you need to implement to respect this additional gauge invariance. So it might be that in future investigations one can just get away without taking into account this explicit gauge invariance, but of course this depends on the observable and the precise investigations that you want to do. So it's not for all of observables this will be the same. Okay, this already brings me to the end of my lecture series. So I've shown you that the matrix models provide an interesting possibility to investigate gauge gravity predictions, which doesn't have the problems that you usually have in the four-dimensional case. The simulations have confirmed in several cases these dualities, and at least for the one-dimensional theories, this precision is rather remarkable. I haven't covered a lot of additional results that are very interesting, especially in 2 dimensions, but also new results are as you have learned also in the research talks, available for the IKKT model. But these kind of things, I think, have been a lot of them also mentioned now in the research talks. And new interesting directions are, of course, quantum computing and deep learning, as I said, which will, I think, play a more important role in the future in these, at least in the one-dimensional models. And the most important thing, especially with respect to this general critique of the mathematical string theory community that I mentioned after the first lecture, that this BFSS model or this formulation of M theory doesn't lead to new mathematics. We are now at least in a situation that new ideas are brought up from the context of lattice investigations and can then be compared to new concepts. It's not really new mathematics, but it's at least something that provides you new insights also on the gravity side. So with that, I want to close.
Thanks very much for the lectures, Georg. And we have time for questions and comments, one of which I see from Navdeep.
Okay, so, well, more than a comment, is a question. Where do you think the numerical methods will really go in the end? So what improvements lie along the line, technically?
I think concerning the techniques and also concerning the computer developments that have also been mentioned by Richard, these, I think, much larger N would be able to achieve, and also the low temperature regime would be able to achieve with much more precision in the future. It's also, I mean, it's rather, the limitation are also how much people want to invest in code developments, because there are much further developments that can be done with the codes, and to reach much larger precision, which with higher improvements. So I think especially concerning the low temperature regime of the theories, you will have much improvements. But then there's also this other question, like, for example, concerning the ground state of the theory, and these can be addressed rather with other methods. Entanglement, entropy, or something like that. And for these kind of questions, I think one has to look at other methods than Monte Carlo simulations. So that's why I mentioned these new developments. So these kind of questions can be addressed there. But I think there's still also a lot of things to study concerning the thermodynamics. For example, to verify in more detail whether we really see this M theory phase at low temperatures. So these kind of things, I think, can still be done with Monte Carlo.
So yesterday there was a comment about sign problem. So we don't see sign problem much in these BFSS and BMN models, but the sign problem is very severe in these IKKT1, but both have the same sort of commutator square. Why is that?
Oh, okay. This is a difficult question. And I think it's not, maybe in a certain regime where you should also see this on the BFSS model. So if you would compactify on a spherical circle, then you should go into somehow a regime where the derivative terms don't matter so much, so that you are led basically to a version of an IKKT-like model. So there must be, I think, certain parameter regimes where you enter also a sign problem for the BFSS model. But apparently this is not the ones that are usually studied with the lattice investigations.
Maybe I can comment on this because it came up during my research talk as well, that the reason we're not seeing sign problems at the continuum limit, at least, is the procedure we go through to take the continuum limit with that fixed dimensionless temperature that puts the bare lattice coupling going to 0 in tandem with the number of sites going to infinity. And if we kept that bare coupling fixed, or in other words, change the temperature with the number of sites, then we would not have that necessarily have that absence of a sign problem.
Yeah, I mean, this depends a little bit. I don't know whether in the IKKT a similar procedure is done. Then
it's hard to talk about a continuum limit with the single site.
Yeah.
So that's why I think it's relevant to that contrast.
Yeah.
Yeah, a question on software. As people know, I am as skeptical as anybody to not waste your time on software if you can do physics first. But on the other hand, is there some place where codes are being shared that's the usual first step and that people can go look at them?
I mean, there are two open software projects. So, I mean, David has one that involves also BFSS and BNN
right.
code.
So, I mean,
and then there's also a Fortran code.
So those links should be sent around. I mean, occasionally you find somebody who prefers to do software, bless their heart, but they have to interact strongly with people who know what the physics is, and the problem has to be settled enough to make it worth it.
Yeah,
but you should look a gift horse in the face.
Yeah, we can.
I mean, like Bootstrap as an example, you know, it's a really interesting thing, but they eventually got some software to use over and over again, and that's why it's become a powerful program.
Yeah, this is true in this example, yeah.
And so, you know, I think this looks to me like it's at the level of maturity and there's enough similarity between the models that this could actually happen, and that makes a big difference. Yeah. Do you agree? I mean, you're an expert, David, so you can fill in on that.
Obviously, I advertised my software quite shamelessly in my lectures.
Maybe I could get a student looking at it, and then I wouldn't have to do
what I will do, because Georg didn't have a link to his own repository, I can put both of those links into the Slack channel for the software inclined to check out. And yeah, actually the SUSY Lattice software, in addition to being advertised in my slides, is also part of the US QCD software stack and linked from all of those web pages that I still have push permissions to even after leaving the US.
I should look at it, but what is the structure of your software? I don't remember. You had started with Milk and then you evolved. Is that what is still sort of like Milk?
It is at the high level like Milk in terms of how you have application directories and the generic directories that implement the single thread library routines.
Right. So in BSM work, you know, people always get stuck in their analysis software. So Milk is still being used a lot, but they call libraries written by the CUDA crowd, right? And so, you know, there can be a handshake, right? I mean, I repeat, you should not waste your time on software instead of doing physics. But on the other, at some point or other, this becomes useful.
Yeah, I mean, David's code is I think, well documented, and you find it. But there's also the link to this Monte Carlo string.
By the way, I think this is sort of official, but Exascale is finished, and there's, I think, gosh, can I say this publicly? Everybody should not pass this on, but there is now.
It's recorded.
Moving on to the next question that's not so confidential.
Yeah, that would be interesting. Yeah. Yeah.
We will look into that when it's we're allowed to.
I mean, in addition to David's code and the code that I've also been developing. There's also Danjo's code. I don't know. This is not public available. Okay. Okay. Yeah.
So I have one question to ask, but I will give others an opportunity to jump in before I.
So there have been discussions about flat directions in BFSS model. So how different is the case in the zero-dimensional IKKT model related to flat directions? Because both have similar kind of potentials.
Sorry? The
Okay,
flat direction in IKKT.
Yes.
Actually, I have never done really simulations of IKKT. I think in principle there are similar problems, and you can even prove that but I think you can prove for a larger number of n that you get well-defined integrals. But for I think SU2 or something, there was a divergence in the integral. So for IKKT, the advantage is that you can use mathematics to really prove the convergence or divergence of these integrals. And there is earlier work. I don't know if Nikolai was involved in, but some people related to that, to these early investigations of IKKT, which have done all this mathematical background.
So I was just going through this M theory paper in which I see a figure sort of when there are like two different plots, one just shows the deconfined and the confined phase, and the other says, okay, we can have a partial confinement also. But the comment is that we argue that the left panel is likely to be true. But if I remember from Hiromasa's talk, he was saying that for irrespective of the order of the transition, he said we do expect partial deconfined phase.
I don't know. I don't have the. Maybe we can discuss it later. But maybe this is basically the picture where you have other as a function. So if you have here, for example, the Polyakov loop as a function of temperature, you have basically two cases. One is where you have a first order transition. First order transition means always that you have an intermediate region where you have basically a metastable second phase. And then this partial deconfined phase should correspond here to this, should be connected like this. And the other case is if basically this temperature and the order of the temperatures is interchanged, that you in that case you have a transition that is higher order. Basically, you see two different transitions. I think one of a second and the other of even of third order, because it's related to this Gross-Witten-Wadia transition. And maybe he was looking at this, and was this your question, why it's not like this? So both of them are have been brought up in this partial deconfinement picture, but one is related to first order, where you have metastability regions, and the other one is related to basically something that looks like a higher order transition, but actually two transitions.
Yeah, I see a T mu plot, some sort of, but we can discuss that later.
Okay, yeah.
Yeah. What is Meyer's transition?
Sorry?
What is Meyer's transition? It is transition between some different phases, or it is something else?
I mean, in the BMN model, you have all these different vacua, and you can have basically a configuration where you are in this trivial vacuum, and then also where you have fuzzy sphere contributions. Basically, these kind of transitions are captured there.
Ah, okay.
Yeah.
Thank you.
So Myers transition is when you have a bunch of D0 branes, and then you insert a flux parameter, a U1 form, and then these D0 branes, they spread in a non-commutative sense, and they localize on the sphere, and this makes it a fuzzy sphere. So from the string theory perspective, this is a Myers transition.
Yeah, this is a gravity picture, yeah, behind the same.
And following up about these two scenarios you sketched on the board, this is the question I wanted to bring up because you skipped over, for lack of time, the Bosonic BFSS work that you and others did a couple of years ago that helped to resolve some debate running over the previous decade about what was the situation in that theory, whether there was just a single first order transition or these two transitions nearby. Given that you have some time, can you tell us a bit about that history and how you resolved those that debate?
We observed basically a first order transition in this range, but before that there have been also investigations of the bosonic theory, but at rather lower n and not doing an explicit check of histograms and hysteresis in this region. And they have found that so in these investigations, usually it was found that it looks like second order. And basically this was this kind of picture that was brought up here. But
yeah, this actually popped up in my lectures last week because I went through the two-dimensional super Yang-Mills phase diagram of the torus as one of the example applications where in the high temperature limit, you expect the fermions to pick up a large thermal mass and then the system to reduce to this one-dimensional bosonic quantum mechanics, which in Euclidean space you can freely interpret as space or time, space or temperature. So it was a nice connection there between that higher dimensional 2D stuff that you mentioned briefly and this investigation that resolved many years of confusion about what exactly was going on in the matrix model that popped up at the high temperature limit there.
Yeah, it would be interesting to discuss how much of this you have seen as well in your simulation.
So let me give one final call for questions or comments about any of Georg's 3 lectures this week. And not seeing any, let's thank Georg again and go for coffee.